Hello class, this is a video tutorial on Permutations Part 4. In this video we'll be looking at selective criteria. This can refer to any condition that requires certain objects to be in set positions. No formula exists for these, as these scenarios are so widely varied. The way to solve these problems is to simply model or simulate the problem. And I'll demonstrate to you this in this set of examples. So we have 5 siblings: Adrian, Beth, Charles, Dan, and Emma, conveniently named A, B, C, D, and E, and they are to be arranged in a line. How many ways can they be arranged if no restrictions apply? I'll start simulating this for the first one. Well, if there's no restrictions that can be applied, how many different people can stand in the front? Well, I know one person can do it, but how many different ways can we put one of these 5 people into the front of the line? Well, there are 5 different ways. If one of them, let's pretend Adrian, stands in front, how many different more ways are left to stand the next person in line? Well, there are 4 different more ways. And then 3, and then 2, and then 1. We've seen this before. This is simply 5 factorial. And there we have it. Now here's the first real unique restriction or selective criteria that we're going to face here. The eldest, Beth, must be first in line. Well, if we were to simulate this, let's pretend Beth is standing in the front of the line. How many different ways can Beth stand in the line? Well, there's only one way, because Beth has to be in front. Well, how many people are left for the remainder? Well, in second place, we have 4 people to choose from. There's 4. And then there's 3. And then there's 2, and then 1. So in total for this one, that's 1, that's for Beth being in the front, times 4 factorial, which we can simplify as just 4 factorial. So notice how we actually just simulate the problem by, well, modeling it. In this case, we said Beth must be in front. Well, we just pretended as if we simulated Beth being in front. And then we continue as normal. So let's keep going with this. A male must be in front of the line. After seeing this example, I hope you can pause it and give this a go yourself, and let's try and figure this out. Well, there were 3 males: Adrian, Charles, and Dan. So let's simulate them standing in the front. Adrian, Charles, and Dan, ACD. How many different ways can a male stand in the front? Well, it could be one of 3, so there are 3 possible ways. Let's pretend it's Adrian in front. So now that we've picked Adrian being in front, how many people are left for the remainder? A common misconception is people say, oh, there are 2 left. Well, that's actually incorrect, because there are only 2 males left, but there's no restriction as to the remainder of the line. It's just that the front must be a male. So in reality, there's actually 4 left in total. We can pick 1 from any of the 4 remaining siblings, and then 3, and then 2, and then 1. So this question is 3 times 4 factorial. And there we have it. So with these ones, you could actually just plug them into your calculator and figure out the actual number, but it's enough for us just to leave it as it is there. You could answer it using the actual number, but it's fine leaving it as it is here. Let's do another one. Here's where it gets rather difficult. The non-identical twins, Dan and Emma, must stand together. So Dan and Emma, let's get rid of this comma, and Dan and Emma must now stand together, no matter what. Well, notice how I simulated that. If they are standing together, how many objects do we have now in total to pick from? We have 1, 2, 3, but now since these are standing together, we treat them as 1. So in reality, we have 4 objects left. So in this first position, how many different ways can we pick from our objects? Well, there are 4. Well, then there are left for 3, and then 2, and then 1. What happens to this last position then? Now remember, one of these selections along the line is Dan and Emma. So no matter where we pick 2 of them, if we choose to pick Dan and Emma, 2 of them will automatically be taken up. For example, if we say the first 2 positions were Dan and Emma, there's that 4, and then 3, 2, and then 1. So notice how because they are in lots of 2, they take up 2 positions no matter when we pick them. So this still holds true. However, so you could really just think of it like this. However, because Dan and Emma are standing together, they could stand together like this, Dan and then Emma, or Emma and then Dan. So notice how we can switch between the 2. So amongst themselves, how many different ways can we organize Dan and Emma? So here's Dan, well, here's the twins, Dan and Emma. How many people can we put into this position if we're only looking at Dan and Emma? Well, there are 2 ways. It could be Dan, or it could be Emma. Let's pretend it's Dan. How many people are left for between the twins? Well, there's 1. That's 2 factorial. And this is 4 factorial. So what this means is, no matter where we put Dan and Emma in this first lot, we could further switch them around and they're still standing together. So in total, we treat them as 1, so that's 4 factorial. And then we treat them as if we can switch them between themselves. So in total, we have 4 factorial times 2 factorial. I'll demonstrate to you this one more time before we move into a new video. For the 3 eldest siblings, Beth, Charles, or Adrian, must stand together. So similar to the first one, since they must stand together, we smush them together like this, and we treat them as 1 unit. Which also means, so that's 1, 2, 3 possible options. Which also means we only have 3 possible positions we need to worry about. So let's think about where we can place these 3 objects. Well, there's 3 for the first one, 2, and then 1. So that's 3 factorial. But now amongst themselves, they can switch between their positions and they're still standing together. By that I mean, we could have them as Adrian, Beth, Charles, or Adrian, Charles, Beth. They're switching amongst themselves, but they're still standing together. So how many different ways can we mix the 3 amongst themselves? Well, we can do a smaller selective criteria. In this first position, how many different ways can we put Adrian, Beth, or Charles? Well, there's 3. Well then, if we put Adrian first, there are 2 people left, and then 1 person left. So even amongst themselves, they can switch further. So on top of the total of organizing these 3 objects, we can organize Adrian, Beth, and Charles further. So in total, we have 3 factorial times 3 factorial. Okay, so that's the first half of this video. We have 2 more examples here, and these get rather difficult. So far, I hope that's given you an insight into how we can model the situation that's being described to us in order to count the total number of arrangements. So I hope to see you in the next video here. Best of luck.